What's up, guys? My name is Michael and welcome to my YouTube channel. Today we're going to talk about stacks in C++ because stacks are one of the best data structures I've ever seen. It has the stack abstract data type and it basically helps you do things that you don't. It's a limited data structure. It's like an array except it's limited, and one of the special things about a stack is that it has limitations. Stacks, queues, dequeues, double-ended queues all have good because they have limitations. And I'll tell you why. The stack is a last in, first out data structure. So if you think about it, let me just explain it like this. Think about it, you're having the stack of plates, right? If you have a bunch of stack of plates, so you add one to the stack, right? So now let's say you add a stack of plates, right? Well, the data structure is like a stack of plate. So you add one to the stack. Let's say you add 2. That adds the number 2 onto the stack. What does that mean? That basically means I add the number 2 into this stack, and now it has the value number 2 in this stack data structure. Now let's say I add another stack, so I push onto the stack. When I say add, I mean push. So I push another number onto the stack. What does that mean? So I add 4. Now 4 is on top of the stack. What I mean by last in, first out, that means I'm talking about basically the data structure basically holds, you could only delete the element on the top, and you could only push the element onto the top. Okay, so like you push last. So so my bad. Okay, so if I push, if I push the number 8 onto the stack, so I push this, so now it's on top of it. When I pop it, so last in, first out. What does that mean? Last in, first out. So that means that an object can be inserted into the stack at any time, but the only most recent inserted, that is the last object, can be removed at any time. So once I push on it, if I want to remove, I only can remove the 8. Okay, I pop. That's called pop. And if I want to remove something, I only can remove the 4. So that pops. Okay, so because it's the last in that was on the data structure, it was the last object that was inserted into the stack at any time, and is the most recent object recently inserted into the stack, and that can only be the one that is removed at any time. The name stack is actually derived from the metaphor of the stack of plates, like I just showed you in a cafeteria dispenser. What does that mean? So that means that the fundamental operations involving the pushing and popping of stacks on the plates. When we add a new plate from the dispenser, we pop the top of that stack. And when we add a plate, we push it down onto the stack to become the new top plate. Perhaps maybe even an amusing metaphor would be a Pez candy dispenser, because they store mint candies in a spring-loaded container that pops out of the topmost candy stack when the top of the dispenser is lifted. Stacks are a fundamental data structure. And why do I say this is good? Because sometimes you don't need the address of every single element. Like when I have a stack, I don't need the number 2 or 4 on the bottom, right? I don't need this. Like let's say there was a number 1 on the bottom. Sometimes I don't need that. So that's the good thing about a stack. It has limitations. It only lets you take out the ones on the top. So I only could take out 8, 4, and 2. And let's say I add number 3. So I only could add it onto the top. I can't add it onto the bottom, and I can't add it onto the front of the stack because, I mean, that's just how stacks works. Okay. Okay. So let's talk about this. So internet browsers store the address of recently visited sites on a stack, and each time a user enters a new site, the site's address is pushed onto the stack of the address, and the browser then allows the user to pop back to previously visited sites using the back button. So text editors normally provide a undo mechanism that could cancel, and recent editing operations that reverts to former states of the document. This undo option is used by a stack. So the reason why it's used by a stack, because it's a good data structure to have. It has some limitations about it. That's a good thing. So these were examples of areas in software that is used by stacks, where they use stacks only. So let's say look at the schematic example of a Pez dispenser. A physical implementation of a stack is registers. You push and pop. That's what it means by a stack. Stack is push and pop. And that's a good thing about stacks. Let's see if there's any more. Oh, okay, so let's go on. So stacks are the simplest of all data structures, and yet they are among the most important, since they are used in a lot of different applications that include many more sophisticated data structures. Formally, a stack is the abstract data type. So you could push the element E on the top of the stack, and you remove the top, you pop. You could push an element E and pop. Pop means remove the top element from the stack, and an error occurs if the stack is empty. Push means to push an element onto the stack, and that occurs when the top of the stack is empty. So what is top? Top returns a reference to the top element of the stack without removing it. An error occurs if the stack is empty. So additionally, let us also define the other elements, such as size. Size returns the number of elements in the stack. And empty empty just returns true if the stack is empty, and false otherwise. So let's see. Here's our following series of stack operations and their initially empty set of stack. So let's talk about it. So let's see what happens. So I'll draw it out like it's a stack of sheets of paper or a stack of anything. Here, let's just draw it out. So let's say I push 5 onto the stack. So here I push 5. 5's on the stack. Okay, this is 5. It's onto the stack. Okay, then I push 3. So now 3 is on top of that. 3 is on top of that 5. All right, it's the stack. Pop. Now 3's gone. Okay, push 7. Let's push 7 on top of the stack. Okay, so 7's on top of the stack. Pop. Okay, so 7's gone. Top, that just returns 5. Okay, top is return 5 because all these are gone. So that's why pop is 5. Okay, so pop is 5. Let's see. Pop. Yep, it's 5. See, I told you. See, I told you that's what it is. Okay. Top is 5. Pop again. Now it's empty. Okay, so now pop again, you're going to get an error. Okay, because this is empty. Now you can't pop nothing because there's nothing there. So you have an empty. All right, let's see. Empty. Well, it returns true because it's empty because there's nothing in here. All right, let's push 9 onto the stack. So 9 is on top of the stack. Let's push 7 onto the stack. Okay, so 7's on top of the stack. So now 7's on top of the stack. Okay, push 3 onto the stack. Okay, 3's on top of the stack. Push 5 onto the top of the stack. 5's on top of the stack. Well, what's the size? 1, 2, 3, 4. 4. So that's why the size here is 4. So now what the stack has is, let's see, from bottom to up, the stack has 9735. 9735 from bottom to up. Okay, pop. Okay, so if I pop the 5 off of the element, so now I only have 973. Pop. And now I push 8 onto the stack. I don't have enough space here, but yeah, just assume there's an 8. Sorry. now I have 8. Pop, I remove 8 from the stack. Okay, so now we have 937. Only 9, 3, and 7 are left. 9, 3, and 7. My bad. This is a thing. Okay, 9, 3, and 7. All right. Top is 3 because this 5 is gone. Okay, so top is 3. Okay, and that's basically it. That was all of the stack. Let's move on to the next. So let's talk about the STL stack. Let's see. Wait, let me see if there's any more to cover in here. So the STL stack is a standard template library that provides the implementation of a stack. The underlying implementation is based on the STL vector class, which is presented before. In order to declare an object of type stack, it is necessary to include the definition file, which is called the stack, as well as STL vector. The class stack is part of the std namespace. So it is necessary either to use the std stack or to provide a using name statement because it's part of std. That's why. So the stack class is templated with the class of the individual elements. For example, the code fragment below declares the stack of integers. So here we do hashtag include the left less than sign, stack, right hand, greater than sign. Okay, so that's the first part of this include statement. This tells us to include the code for stack, so then we could use the stack of STL. Now we using std stack because we want the code from std necessary in order to use the stack. Now we could create our stack of integers. So now it's stack less than sign int, right hand sign my stack. So we refer to the type of individual elements as the stack's base type, and that's what this integer is, as well as STL vectors, and STL stack dynamically resizes itself as new elements are pushed on. The STL stack class supports some operators as our interface. Below we list the principal member functions. Let S be declared to be an STL vector, and let E denote a single object whose type is the same as the base type of the stack. For example, S is the vector of integers and E is a integer. Okay, so let size returns the number of elements in the stack. Empty returns true if the stack is empty. So these are the same functions. Push pushes the E on top of the stack. Pop pops the elements at the top of the stack. Top returns a reference to the element on the top of the stack. So this is a significant difference between the STL implementation and our own definitions of the stack operations. In the STL implementation, the result is either of the operations are top or pop to an empty stack is undefined. In particular, no exception is thrown. Even though no exception is thrown, it may actually result in your program aborting. So the difference about this implementation is that it actually there's no exceptions thrown. Okay, so even though there is no exception throwing, the program might abort itself because it just crashes. Thus, it is up to the programmer to determine if there's no such illegal accesses are attempted. So let's talk about the stack interface. So before we discuss the specific implementation of the stack, let us first consider how to define an abstract data type of the stack. So we define a data type. We define this principle as concerned by the application program interface. And what does that mean? That's called the API, application programming interface, or simply interface. And this just describes all the methods that ADT must support and all the names of the public methods and how they are declared and used. An interface is not a complete description of all the public members. For example, it doesn't include the private data members. So when we talk about APIs, we're talking about the application programming interface. That just gives us all the methods and functions we could use for our stack. Any API of any code you're using, it basically it just tells you the public members of what you can use. Okay, they don't let you access the private data members. So that's it's another part of encapsulation about why APIs are good, because they basically tell us, okay, you could only use this code and you don't have to know how it works. You just have to know this code does this thing, and you don't need to know anything behind it. It's anything under the hood. You just use this code and do whatever you want with it. Okay, that's a good thing about APIs. So the reason why I told you about this is that in the stack STL, well, it has a list of members that any implementation must provide. The C++ language does not provide a simple method for defining interfaces. Therefore, the interface defined here is not an official C++ class, and it is offered principally for the purpose of illustration. So the informal interface of the stack ADD is given in code fragment 5.1. This interface defines a class template. So recall from the section that a definition implies that the base type of an element being stored in the stack will be provided by the user. This element type is indicated by E. So E can be any fundamental type, such as int, char, boolean, and double, and any built-in or user-defined class, or a pointer to any of these. So here, let's talk about E. Template type name E. Class state stack public int size const bool empty const E reference top const throw stack empty. So these are just the whole interface of all the public methods and all the methods that you could use, and basically they tell us what we could do. Okay, so basically what are we doing here? Basically the E, they're telling us that E can be a fundamental type of any type, and these fundamental types basically allows us to declare a stack of any different types, such as int, char, bool, and double. And these types, you could even define your own user-defined type, and this is called templates. And we've seen this before in a bunch of other data structures for vectors, and we've seen it before for linked lists and recursion, sadly recursion, which I definitely cannot figure out that simple question about reusing templates, because for some reason it's just not working for me. But anyway, let's continue on. So observe that the member function size, empty, and top are all declared to be const, which informs the compiler that they do not alter the contents of the stack. The member function top returns a constant reference to the top of the stack, which means that its value may be read but not written. Note that pop does not return the element that was popped. If the user wants to know this value, it is necessary to perform a top operation first and then save the value. So what does that mean? Basically, pop doesn't return the element that was deleted, right? It just deletes the top element, right? So if you actually want the top element, you have to call top. I'm sorry about this, but STL doesn't allow you to, like, when you call pop, it doesn't return the top element that was deleted. It just deletes the top element. So you have to call top if you want to know what before you call pop, if you want to know what element was deleted. So that's the problem. That's what this paragraph is talking about. So that's, you have to do a top first and then save the value. So and then print it out if you want to know what was deleted when you call pop. Okay, so the member function push takes a constant reference to an object of type E as its argument, and recall that that is the most efficient way of passing objects into functions. You have to pass them by reference, mainly because, remember, references are just another name, an alias for the name of the whatever the original object was, or type whatever it was. And so when you pass it with the ampersand, it's the most efficient way of doing it because you now have the exact location of that current object that you were doing. So then when you pass it in, it's easier to use. Okay, so let's talk about this. An error occurs when calling either a function pop or top on an empty stack. So what you can do is you could create an exception of type StackEmpty, which they define here. Basically, it is an exception thrown on performing a top or pop of an empty stack. So here's a class StackEmpty, and it basically is inherited the code of runtime exception. And runtime exception is another exception that I'm guessing they defined. I don't know if this is a thing in STL because, runtime exceptions, you don't know what they are. But anyway, basically, they just declare their own StackEmpty exception, and they throw this exception when there's an empty stack occurring, and then when you call pop or top on an empty stack, because you can't really delete nothing, right? If you delete nothing, that just doesn't make sense. So that's when empty condition occurs, right? But the thing is, in C++, there's no error that tells you what happens if you delete nothing, right? So that's why they created a StackEmpty exception, and this is thrown when the functions pop or top are on an empty stack. And that's what they are doing here. Let's talk about another thing. So how do they implement stacks? Well, inside the STL, they did a way to implement it there's a few ways you could do it. You could do it with arrays. And you can implement a stack by storing its elements in an array. So specifically, I'm guessing I don't know if they actually do this, but this is one way you could do it. I don't know if STL actually does this, but specifically the stack has an implementation of whatever elements you have plus an integer variable t. So you have this array of 0, 1, 2, 3, 4, 5, 6 elements, right? And realization by stack of it's an array, right? The top of the element is always stored as s of t. So the top of the element, which is the last thing that you pushed on. So let's flip this over, okay? We're going to flip this pushed thing on over, okay? We're going to flip this all over. So what does that mean? So basically, remember we said push. Let's say we push 3 onto the stack, okay? We push 3, right? We push 3, then we push 4. Push 4 onto the stack, okay? Then we push 5. I don't know where this is going, but let's say we push 5, right? We're basically adding to the top element. And a way you could do this is think about it as flipping. Let's just select this and rotate it. All right, we're going to rotate this to the right. Okay, so this is basically a way you could implement it. You could think about implement it as an array, where the top, and whenever you push something on it, you add it to the right, to the next element in this array. So then at the last element, the top t, the last element that you added, right, it would be stored at s of t. So here at the element 5, it would be stored at 0, 1, 2. So whenever you add something, you would just have the element of whatever you added. Say I want to push 7 on it. It would just be stored on the right of the array, right? And we're assuming that the array has, it doesn't go over the size. We're assuming that the array, it holds the perfectly good amount of numbers, right? So that's what they're saying here. They're saying that you could have the top element, which is the last one that you pushed on, and have that stored at the end of the array, which is s of t. So that's what they do here. Recall that arrays in C++ start at index 0, and when we initialize t to -1, we use this value of t to identify when the stack is empty. Likewise, we could use this variable to determine the number of elements in a stack t plus 1, and we also introduce a new type of exception called stack full, which is indicate if we insert a new element when the array is full. Okay, so originally I told you about arrays that the problem about arrays is that resizing arrays, right? That's a huge problem about arrays. Well, what they're doing here is that if you keep pushing onto the element and it goes past the size of the array, they're going to throw a stack full exception, which is not really a thing in C++, because I'm guessing they have a way to resize in STL, like in STL's implementation of C++. But let's say we're not resizing the array, okay? Let's just say we're not resizing it. Then we have to throw an exception when the array gets full and you can't add any more elements to it, right? So that's what they do here. They throw an exception called stack full, which is what they define here, and to implement their stack, and it's defined in StackAtd. Given this new exception, we could implement the StackAtd functions as described in code down here. So here's all the algorithm. Okay, so they basically have an index t, which is the last element that was added. The size would just be the last element added, their index plus 1, right? So t is going to be the index of whatever last element added. So if I added another element here, let's say I added 8, right? I pushed 8 onto the stack. Well, the last element would be index 4, 0, 1, 2, 3. And the size, well, there's at index 4, right? The size would just be plus the index of whatever the last element plus 1, because think about it. Look, if I add another element onto the stack, well, I had the last element is 4, right? Well, I have to there's now 5 numbers in this stack. So now it's 4 plus 1, which is 5. So that's what the last element is size. Okay, you could check if the array is empty by checking if the index is less than 0. So I'm guessing they're starting the index at -1 as their index or something like that. And whenever they add a new element into the array, they add they basically return if it's less than 1. No, to check if it's empty. Yeah. Whenever they add something to an array, when they push it onto the array, they increment t and then they add it at that t. So I'm guessing, yeah, if just checking it empty, it's gonna check if the index that you're adding at is less than 0, because they start it as less than 0. And yeah, that's what they're doing. Top basically just checks if it's empty, and then it throws a StackEmpty exception, and then it returns whatever at the last element of t, which is what we showed before, just the last element. Well, top is going to be this. Like if you rotate this back to the left, this should be, yeah, back to the left, this is going to be 8, right? Well, the top element is 8, right? And basically that's just s of t. T is the last element that was in this array, so they just return s of t, assuming if it's not empty, okay? Push, if it goes over the stack, they throw the stack full exception, right? If it doesn't, they just add t by 1, which is the index of the last element, which is 4 plus 1, which is 5, and then they just add what? So let's say I push 9 onto the stack, right? This would be at index 4 plus 1, which is 5, at index 5, 9. This is really, you can't read that at all, but sorry guys, that's basically what it was. Pop, they don't actually remove the element. They just decrement the size, which is a stupid way to do it. They actually should take out the last element and set it to null or something. They should really just take out this last element and set it to whatever it was. Okay, so the correctness of the functions in the array-based implementation follows immediately from the definition of the function itself. The running times for member functions in a realization of a stack by an array. Each of the stack functions in the array realization executes a number of statements involving stack arithmetic operations, comparisons, assignments. Thus, in this implementation of a stack, each function runs in constant time. That is, they each run in O of 1. Yeah. They all run in O of 1 mainly because of it. Just each operation just takes, doesn't take anything. They're not resizing anything, so I'm guessing that's why. Let me get a drink of water first. My throat is parched right now from all this talking. Water is good for you. It's good for the throat. Really good for you. Okay. So now they provide a C++ implementation of a stack. And here, they're going to call it an array stack because they're using an array to implement the stack. So to keep the code simple, we omitted the standard housekeeping utilities such as destructor and an assignment operator and a copy constructor. So let's leave their implementations as an exercise. What? Wait, so they want... Okay, so I'm guessing they're... Wow, they're forcing us to code it. Okay, but it doesn't matter though. Okay, so in addition to the member functions required by the interface, we also provide a constructor that has a default size of def capacity, and I think that's of 100. Def capacity of 100. Okay. Oh, they do have an implementation. Okay, so this is an example of a default arguments in a function called enumeration. Define this constant value. Okay, the simplest way of defining. Okay, so the maximum size they use the constant value. This is just all explaining it. Okay, def capacity. So they initialize it with the size of def capacity. To have 100, initialize the array to have 100. Just with the name def capacity, just because this is better. This is good because it's a constant value and it basically allows you to define your constants, right? So if you change the name of def capacity or change the value of def capacity, it changes the code. Someone's actually messaging me right now, so let me just get that. All right, back to the code. This is the simplest way of defining the okay, so that's what they do here. Okay, so the constructor allocates the array size, which is def capacity. That makes sense. New e cap def capacity. Okay. Yeah. Pop and push, check if it's not empty, otherwise returns an exception. Similarly, push checks if the stack is not full and it throws an exception. Okay, so this is all their implementations, okay? This initializes the array. This initializes the capacity, which is just the default size. I don't know. Yeah. Let me just go check what they meant by capacity. Yeah, the stack, the total size of the capacity. Yeah, and then they initialize the starting index to have -1. I mean, the reason why I do this, remember I told you when you add 1, each time they're just going to add 1, and then they're going to, at that location, to set that value to have that. So that's where they start at -1, because if they start at 0, then their last index would be would go out. That's the reason why. Okay, so here, let's just talk more. Here we have the, here. So size, it returns t plus 1. T is the index of the last element added. T is less than 0. This is basically checking if the stack is empty. Is the stack empty? Return s of t. Yeah. If it's not empty, do it. Push element onto the stack. Pre-decrement. Yeah, they pre-decrement t and then add it. Okay. Yeah, pop. They don't actually delete the element. They just decrease size by 1. Okay, that bugs me out. Okay, here's a fragment of what they're doing with their array of stacks. Push 3, 7, push 13, get the top. That's going to be 13, right? Yeah, 13. Pop it. Okay, now that has only 7, push 9, it's 7, 9. Yeah, size of 2, 9. Then now they print out the top, which is going to be 7, 9, right? Well, it's going to be 9 both times because they didn't remove 9 here, and then they popped it though, so now it's 9 is gone. Okay, so this, you could also use strings. They're just demonstrating strings here. Whoops. This just demonstrates strings. Okay, so note that our implementation, while simple and efficient, could be enhanced in a number of ways. For example, it assumes that the fixed upper bound n on the ultimate size of the stack. In the code, we choose a default capacity of n equals 100, more or less arbitrary. An application may actually need much less space than the given initial size, and this would be wasteful of memory. Alternatively, an application may need more space than this, in which case our stack implementation might crash if too many elements are pushed onto the stack. Okay, so that's just what they're saying. Yeah, why don't they use a vector? Fortunately, there are other implementations that do not impose an arbitrary size limitation. Yeah, well, they should use you're going to use a stack class to implement a stack. That doesn't make sense. You can't do that. That's cheating. Why else would you? Okay. Another one is, okay, yeah, make a vector. Use vectors. It offers an advantage that is automatically expanded when the stack overflows with current storage. Yeah. So, yeah, STL Stack would be easier way to implement a array-based stack. That doesn't make sense. You can't use you can't use their stack to implement your own stack. That doesn't make sense. Okay. Initially, you could have a good estimate number of elements needed to go in a stack. An array-based implementation is hard to be from a perspective. Stacks serve as a right role for computing applications. Okay, so yeah, that's what stacks are. Another way to implement a stack is using a generic linked list. Wow. Okay, so you could use a generic linked list. So basically, an approach is to use a generic linked list is called, they're going to use a single linked list, which was presented earlier. The definition of the stack called linked stack, which was presented earlier. To avoid syntactical messiness to implement it in templates, they chose not to implement a fully generic template class. Instead, they opted to define a type for the stack's elements called element. In this case, they're going to define element to be type string, and then leave the rest to have your own generic implementation as an exercise. So yeah, these are all the same functions as the same link, same thing as the same thing as the stack, all the same methods as before. Okay, so the principal data member of the class is the generic linked list of type element called S. Since the S-link class does not represent and provide a member function size, you could store the current size of the member variable n. So here you represent the implementation of this constructor and size and empty functions. Our constructor creates an initial stack and initial size n to 0. So they don't provide a explicit destructor. Instead, they rely on the destructor to deallocate the linked list. Okay, so they don't provide a destructor. They just rely on the single linked list destructor to deallocate it. So here they have the, okay, so to the top of the class, if it's empty, they return the front. If it's not empty, yeah, if it's empty, they throw a stack exception. If it's not empty, they throw the front. Push, they increment the size of it and then add it to the front, which I guess that would work. Yeah, that would. Okay, that would work. So this is basically, if you have, remember 3, 4, 5. Let's say I add push 3 onto the stack, push 7 onto the stack, push 8 onto the stack, right? So remember that example. Instead of doing, let's just rotate this right to the right now. Instead of doing, whoops, damn, my fault. Let's rotate right. Instead of making it like this, where the last element represents the top of the stack, they're going to actually add to the front. So what that means is, if I push 3 onto the stack, 7 onto the stack, and 8 onto the stack, they're going to translate this as, I'm going to add 8 to the, so this is going to translate as, originally it'll be, I add 3, then I'm going to add 7 to this. So this is equal to, I'm going to add 7 to the front, then I'm going to add 8 to the front. So when you do push and pop, they're actually adding to the front. That's what they're doing. That's how they're implementing this. So they're going to add it to the front, and popping, they're going to remove from the front. So if you pop, they're going to remove this. So 8 is gone, and then 7 is gone. So yeah, you could reverse a vector using a stack. How would you do it? Well, you could do this by, if you reverse the vector using a stack, you produce a non-recursive algorithm here for the array reversal problem. Basic idea is to push all the elements of the vector in order onto the stack and then fill the vector back up again by popping all the elements off the stack. So here's how it works. You push all the elements onto the stack, and then you pop all the elements in reverse order. And I'll just show you how this works. So if my input vector was Jack, Kate, and whatever, let's say I have a list of, let's say, Jack, Kate, and T, whatever, Tony, whatever. This is my input vector, right? And I want to reverse it to make T, K, and J, right? Well, you would push all the vectors onto the stack, which you have J, K, and T. So this is now the stack, right? And then you could keep popping it So now you push all the elements on the stack, right? So now you have set your new array to have whatever's on top of the stack and then pop. So now my new array is going to have whatever's on top of the stack, T, pop it. And then I'm going to have whatever's on top of the stack, K, pop it. And then what's on top of the stack, J, pop it. And that reversed your vector, your array or your vector, whatever. So now the array contains a different thing, reversed. Another thing you could do is, here's a cool exercise you could do. HTML tags. So you could explore two related application stacks. The first is matching parentheses and grouping symbols in arithmetic expressions, such as arithmetic expressions can contain various parts of grouping symbols like parentheses, braces, brackets, fuller symbols, ceiling symbols. So if you want to group them, you do correct. This is the correct way to do it. The left bracket must match the corresponding right bracket for the expression. So if you want to group it the correct way, this has to match this, this has to match that, 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 this has to match that. This is incorrect. This is incorrect because this symbol has to match this symbol, and it doesn't. So a way to do this, here's a cool problem, which is the braces matching. A way to do this is using, guess what, stacks. So you have to make sure the grouping symbols match up. You can use the stack to store the matching symbols from left to right. Suppose we're given a sequence of whatever it is, and it's a token, a variable name, an arithmetic operator, or a number. Basic idea is checking that the grouping symbols in S match correctly. Is a process of tokens in X in order. Each time we encounter an opening symbol, we push that symbol onto the stack. As in each time we encounter a closing symbol, we pop the top of the symbol from the stack. And we check that these two symbols are of corresponding types. For example, if the symbol, this parentheses was pushed, then the symbol this should be matched. And if the stack is empty after we have processed the whole sequence, then the symbols in X would match. Assuming that push and pop operations are implemented in a run in constant time, the algorithm runs in O of n time. So yeah, so here's how they do it. Given an array X of n tokens, each way is a grouping symbol of arithmetic operator or a number. Return true if all the grouping symbols in X match. So let S be an empty stack. So we're going to loop through from I to n minus 1. What is n minus 1? N is the whole string. So given an X of n tokens, they're taking the whole string, which is, I'm getting really tired, but it's this whole thing. So they're going to loop through the whole thing, right? Loop through the whole stack. If X at I is an opening symbol, then you push it onto the stack. So they loop through the whole array of the string. They go loop through the whole string, right? Get each character. If it's a matching symbol, they push it onto the stack. Otherwise, if it is a closing symbol, then check if it's empty. If it is, you return false. There's nothing to match with. Check if the top matches with it. If it doesn't match with it, return false. Then otherwise you pop. Okay, if it does match, you pop. Okay, then if it's empty, return true. Otherwise, return false. So that's how you would work. You could do this in HTML tags. That's how they would use it. Here it just checks if you store the right amount of tag using stacks. It's pretty decent. I don't feel like explaining how this works. It's just loops. It's the same thing what I showed you. It loops through it and then checks if it's the top of the thing is matching. That's what they're doing. Okay. Alright, so let's talk about queues. And queues are they're the same as a stack. Whoops. But the queue is basically a line. So they're like a stack, but it's different. Okay. Another data structure. Let's talk about queues. So basically, what is a queue? A queue is basically a line. Okay. Think about it's called first in, first out. And why do I call it a queue? Well, a queue is the same thing as a queue in you know, in Europe, in whatever it's called. It's called, this is a line. Okay, my bad. So let's say I add, let's say I have one person standing in line. Okay, this is my person. All right, let's call him Bob. All right, so he's standing in line. And when you add another person, this is call him Joe. This is, not Joe. Let's call it Sarah. Okay, this is Sarah. And she goes on the back of the line, and she joins the line. Well, who leaves first? Well, in the line of Joe, Bob, and Sarah, and let's call her Jessie. You like my hair? The fabulous Jessie. And then let's call this person. I'm gonna make her have those hair buns, those ties. Okay. Jessie. Let's call her Jessie. Okay, so this is gonna be Joe, Sarah, Bob. This is a guy. Jessie. Jessie. Okay, so they're waiting in the movie theater, right? So whenever a new person comes to line, they have to wait in the back. So that's basically what a queue is. They wait in the back, and whoever was first gets out first. So Joe gets out first. Then when they walked into the line, well, Sarah's gonna get out, Bob's gonna get out, Jesse's gonna get out, and then whoever's last in line will get out. So that's basically what a queue is. It's a first in, first out data structure. And elements can be inserted in a queue at any time, but only the element that has been in the queue the longest can be removed at any time. We usually say that the elements enter the queue at the rear and are removed from the front. Metaphor for this terminology is a line of people waiting to get something from the amusement park, and that's what I just showed you. So how do we do this? Well, the queue's abstract data type. The queue abstract data type defines a container that keeps the elements in sequence, where each element access and deletion is restricted to the first element of the sequence, which is called the front of the queue. And the element insertion is restricted to the end of the queue, which is called the rear. And this restriction enforces a rule that says that items are inserted and deleted in a queue according to the first and first out data structure. So NQ means insert at the rear at the end. So when I NQ, Jesse was NQ'd in the back, so I inserted to the end, right? And DQ'd means removed from the front. And error occurs if the whole list is empty. Whole queue is empty. Front returns the front and doesn't remove anything. And you also have a size and empty. Size returns the number of elements in the queue. Empty checks if it's empty. So let's look at this queue. Let me just delete this. And let's just go over what the data structure of this looks like. So let's say here, NQ, let's say I NQ, right? So that adds to the back 5. Well, there's nothing in the queue originally, so adds to the back 5. NQ again, add to the back 3. Okay, front, this is going to be 5 because it's 5. It doesn't remove it, right? Size is going to be 2. Yeah, there's 2 elements. DQ, I removed from the front, so I have 3. And that's the reason why there's 3s left. There's only 3 in the array now. Not array, in the queue now. NQ, add to the 7. So now the queue has 7 in it. DQ, remove from the front. So now it's only 7. That's why here it only has 7. When you call front, that just gets the first element of the array in the queue. So that's 7. And that's why there's nothing in it, right? DQ, remove this. And now it's basically empty. DQ, you get an error again. Empty, it just returns true. So that was basically a queue. Let's talk about the STL queue. The STL library provides an implementation of queue, as with the STL stack, and the underlying implementation is based on the STL vector class. In order to declare an object of type queue, it is necessary to include the definition file, which is called a queue. As with the STL vector, the class queue is part of the std namespace, so it is necessary either to use the std queue or to provide an appropriate using statement. So the queue class is templated with the base type of the individual elements. For example, the code fragment below declares a queue of floats. Here, yeah, you have to do hashtag include queue in order to use your queue using std name queue to use a queue, and here's a queue. That's how you declare a queue of type floats. And yeah, here's all the elements again. Unlike our queue, their queue also provides access to the front and the back. So they have a front and a back. Similar to the stack, which the result of applying any of the operations front, back, or pop to empty STL is undefined. Unlike our interface, no exception is thrown because they don't throw in exceptions for queues. So it's up to the programmer to make sure that no illegal accesses are attempted. Yeah, let's talk about, this is the interface, which is all the methods that we have. Exactly. Yeah, this just returns the front. Yeah, okay. So this is all the methods that we have. Abstract, template, it's templated. Let's just go to the next. So yeah, as with the same thing before, if you queue, if it's empty and you try to, what was it, dequeue, I think, remove from an empty, C++ basically doesn't tell you if it crashes or not, so that's why they have a queue empty exception, which they created it, extends runtime exception, and yeah, that's what they have. So how do you implement a queue? Well, a way to do this is to use an array-based implementation, and one way to do this is just store all the elements. Same thing. Let 0 be the front of the queue and have the queue grow from there. It's not efficient, but it requires that we have to move all the elements forward one array each time we perform a dequeue. This would require O of n to perform the dequeue every time, where n is the number of elements in the queue. Another thing, you could use use an array circularly. So to avoid moving elements that are placed in queue, you could define 3 variables, where you basically, f is the index of the queue storing in the front. If it's not empty, then the index of this element can be removed by dequeue. R is the index of following the back of the queue, and if this is not full, the index where the element is inserted by the end queue. N is the number of elements in the queue. So initially we set nf and 0 to all, nfr 0 to all have 0. Then when we dequeue an element from the front of the queue, we decrement n and increment f. It's the next cell. Likewise, when we enqueue an element, we increment r and decrement n. And this allows us to implement the enqueue and dequeue functions in constant time. So how would this work? Okay, so there's still, okay. So let's say I have let's say I have, I don't know, 3, 5, and 7 again. 3, 5, 7. So if I want to enqueue, which is to remove the, to add something to the back, right? What would they do? Well, they have an index to store R, which is at the back, and this is, so if I enqueue, I just store the index at R. So this would be 8. If I want to add 8, I'll just add index, add 0, 1, 2, 3, 4, 0, 1, 2, 3, 0, 1, 2, 3. 3, this would be the index, right? And they also have an index to the front, which is, if it's not, it's the front of the queue. If the queue is not empty, this is the index of the element to be removed by the queue. So this would be front, I don't know, 0. And n is the current number of elements in the queue, right? So if you want to dequeue an element from the front, you increment n and decrement f in the next cell of, wait, n is the current number of elements. So you decrement n, yeah, so the number of elements gets decreased, and you increment f. So now f is now starting at here. So the starting point of f would be 1. So they don't actually remove this. They don't resize. They just let 3 still stay there. Wow. And they're just going to assume the next one's going to start at 0 now. That's what they're doing. They're basically just saying, I'm not going to delete it, and I'm just going to increase the next starting index to start from 1 instead. And then if I want to delete it again, dequeue it again, I'll just have the next index start at 2 instead whenever I loop. Okay, that's pretty ridiculous, but whatever. Yeah, this would have an out of bounds error. If you insert element just one more time, you might get an array out of bounds, even though there is plenty of room in the queue in the case. To avoid the problem, you could try to utilize all of the array, which you could wrap the elements around the end of the queue. That is, now we view queue as a circular array that goes from queue of 0 to queue of n minus 1, and then go back to queue of 0 again. Yeah. Yeah, you could wrap whatever elements that was gone back to 0 again. I don't know how that would work, but you could mathematically do something. Yeah, here they do it. They use a modulus operator. Each time we increment f, we simply compute the statement f plus 1 mod by n. F plus 1 mod by n, where the mod is the mod operator. Take the remainder of the... Yeah, you take the remainder of the function. Okay, so what are they going to do? We have introduced a new exception called stack queue full. Okay, yeah, we know that. So this way is quite efficient. I don't get how. All the operations are performed all of one. Well, I guess so if you're not wasting space. So, yeah. The only advantage, the real disadvantage of the array-based queue is that we artificially set the capacity of the queue to be some number n. In a real application, we might actually need more or less queue capacity than this, but if we have a good estimate of the number of elements in the queue at the same time, then the array-based implementation is quite efficient. One such possible application of queue is dynamic memory allocation. Oh, okay. Okay, so if it's empty, it's 0. Size, return n. Yeah, I know. Front, if it's empty, return the index of the front. Yeah, I know that. Dequeue, they just increment. If it's empty, they throw. Okay. They add 1 and then mod by n. What? So they add 1. So if I have 3, 5, and 7, I want to add 1. Okay, so I want to remove 3. So 3 is going to... I add 1 to f, right? So originally f was 0, add 1, so now it's 1. Mod by number of n, which is 3. 1 mod by 3 is 1. Okay? So f is going to equal to 1 now. How does this wrap around? That's what I don't get it. Okay, whatever. It is mathematical voodoo. Okay. N equals n minus 1. Okay. Yeah, this decrements the size. Okay. NQ, yeah, you're adding to the back. Why? I don't get it, but apparently it makes it more efficient. A better way to do this is to use a circular linked list, which we presented before. So recall that you could, the good thing about a circular linked list is how it was maintained, that it was circular. The n goes back to the front. So recall that in circular linked lists, it retains a pointer called cursor that points to one end of the list. And recall that it provides two members, back and front. So the front back returns a reference to the element to which the cursor points, and the function front returns a reference to the element that immediately follows it in the circular linked list. So in order to implement a queue, the elements referenced by back will be the rear end of the queue, and the elements referenced by front will be front end. So here they have front and rear, right? So recall that circular list supports the following modifier functions. The function add inserts a new element after the cursor. The function remove removes the element immediately following the cursor. So this was a queue, not the queue. This was the circular linked list, and if we want to implement a queue, well, you just they're gonna just do this to implement a queue. They're just gonna to remove the front. They'll just call the circulars next, cursors next. Remove the rear. They just set this to equal to back to the front. This next to point back to the front. So it's just that's a good thing about it, is that this would actually make it way more efficient. So remove after the cursor, remove the front. As shown above, to avoid syntactical messiness, they just chose to regular template class. Okay, so here, if you, so here, if they wanted to dequeue, right? So they're gonna remove from the end. So what do? They originally it was boss here. They're just gonna set. Oh no, this is not dequeue. This is adding to the rear, right? This is enqueue, right? So they want to add boss. So they just set the rear end to point to boss and have boss point to the front. That's what they're doing. And then the cursor advance it to the next. Yeah, that's what they're doing. And to delete and to dequeue, they just set cursors next to point to fronts next. So fronts next was MSP, and cursors next is now going to point to MSP. And then they're going to delete the front, which is lax. So here are all the methods again, which is the same as the other one. Difference is that now we're using a linked list. So initialize the size of 0. They're not doing anything in constructor. Size, this is the constructor, right? They're not doing anything. Size, they're going to return n. Empty checks if the size is 0. If it's empty and you're returning the front, it's going to throw an exception of queue empty. Otherwise, they just return c.front, which is the front of the queue. Enqueue, you just add e to the front. No, to the back, right? Add to the back, and then they advance the c pointer. So because we already implemented adding to the back and adding to the front for the circular linked list class, they could just call c.add onto for the function add for the circular linked list. Remove, they just call c.remove, which removes from the front, and this is just the same function that was implemented in circular linked list. Observe all the functions are implemented over one time, therefore this implementation is quite efficient, unlike the array-based, expanding dynamically. Okay. Alright, let's talk about double-ended queues, and this is going to be the last part, and I'm going to get another drink of water before I talk about double-ended queues, because queues are amazing. Aren't queues amazing, guys? So now let's talk about double-ended queues. And what is a double-ended queue? It's the same thing as a queue, except now you could add from the front, add from the back, and delete from the front and delete from the back. Think of a double-ended queue like a double-decker sandwich. It's good on the front and the back. I guess maybe that wasn't a good analogy. Okay, so yeah, you could insert from the front, you could insert from the back, you could erase from the front, you could erase from the back. So you could also return from the front, return from the back, return the size, get the, excuse me, return true if the dequeue is empty, or false otherwise. So let's do this. So let's just delete this, and just try it. Let's see. Insert from the front. So I'm going to insert from the front, 5, insert, get the front. Okay, so it's going to return 5. Erase from the front, 5's gone. Okay, insert from the back, get the back, which is 7. Erase from the front, erase from the back, it's going to be empty now. Okay, see, easy peasy lemon squeezy. So STL also has their own dequeue. As with stacks and queues, STL provides the implementation of a dequeue. Underlying implementation is based on the STL vector class. The pattern of usage is similar to that of the STL Stack and the STL Queue. So first we got to include the file Dequeue as it is of any stack queue. You have to use the using names, the using std statement Dequeue to make Dequeue accessible. And then this is how you create a Dequeue. String or whatever your type it is, and then my Dequeue. Alright, so yeah, these are all the things. Add to the front, push front, insert it at the beginning, push back, insert at the end, pop front, removes from the front, pop back, removes from the back. Front returns the front, back returns the back of the element. If you do push back, so similar to stacks queues, the results of applying any of the operations of front, back, push front, or push back to an empty STL queue is undefined. So thus no exception is thrown, but the programmer may abort. The program may abort. So yeah. Yeah. So let's do this. Implementing a DQ with a doubly linked list. So as she shown before, you could also implement the DQ using a doubly linked list. Reason why it's a good way, because you have access to front and the back, and you could go through the whole linked list, do previous and next, place the front of the DQ at the head of the linked list and rear at the tail. So like what you see here before, head, next, previous, next, previous, next, previous, next, previous, tail. The front of a DQ is stored just after the header at JFK. The back of the DQ is stored just before the SFO. Back, front, okay. Alright, all of these are all the functions. Insert back, insert front, remove back, remove front, back, front. These just return they return. They give you the element at the front and they give you the element at the back. Size just returns the size of the number of elements in the DQ. Empty just returns if it's empty, and yeah. Remove front, remove back. Throws an exception if there's no front and back. That's why. We're not bothered with the explicit destructure because we're assuming that it automatically deallocates memory. So yeah, most of the member functions for the DQ class are straightforward generalizations of the corresponding functions of the link queue class, so we omitted them. So add front, we just call the DQs add front, DQ add back, just calls the DQs doubly linked list add back. If it's empty, throw an exception. Remove front, subtract the size, move back, subtract, add it, yeah. So yeah, you can realize they all run at O of one time. Okay, now let's talk about adapters and adapter design patterns. So an inspection of the code that we saw reveals a common pattern. In each case, we have an existing data structure and we adapted it for a specific purpose. And we showed how the doubly linked list class could adapt into implement a DQ. Except for the additional feature keeping track of the number of elements, where we have simply mapped each DQ operation insert front to the corresponding operation of the linked list, such as add front. Adapter, also called a wrapper, is a data structure. An adapter, also called a wrapper, is a data structure. For example, a class in C++ that translate one interface to another. You can think of an adapter as a software analogous to an electric plug-in, which are used to keep when you want to plug your electric appliances into electric wall sockets in different countries. So an adaptation we observe is possible to implement the StackEmpty by means of a DQ data structure. So that is, we can translate each stack operation into a fully functional equivalent DQ operation. Structure mapping is represented here. So size returns a size, so you could have your own DQ implementation. Empty, top, front, push O, insert front, pop, erase front. Note that because of DQ symmetry, the performing insertion and removal from the rear of the DQ would be equivalently efficient. So likewise, we could discover correspondence for the queue abstract data type, as shown here. Size, empty, front, insert back, erase front. So as a more concrete adapter design pattern, consider the code fragment shown here. In this code fragment, we present a class DQ stack, which implements the stack abstract data type. Its implementation is based on the translating each stack operation into the corresponding operation on the linked DQ, which we observe here. So here you have a DQ stack, and you could have all these operations: push, pop, top, empty, size. Now, you could have the implementation of stack by means of a DQ, and these are all the implementations of a DQ of the stack. So yeah, what was the adapter? Basically, it basically allowed us to write one interface to another, and that's the design pattern of adapters. They didn't go over it. So we took it existing data structure and adapted it for a special purpose. So that's what the adapter pattern, design pattern is. Use something else and you try to adapt it to another purpose. Anyway, these are all the exercises. Man, I hope I don't get stuck on these exercises like the other one. But yeah, I hope you guys enjoy this video. Prepare to comment, subscribe.